Welcome to lecture 2 of our Twitch stream on structural steel design. A couple of housekeeping items. So first off, the attendance grades are up to date. If there's an issue, I know that we've had some students register. If there was an issue there, let me know. Don't forget the poll on Teams about the manual. I'll say this: I actually went ahead and built all the homeworks and the solutions for next week. And there is one assignment where you can pretty much do the assignment with the resources that are on Blackboard. There is one table in the manual that you would need. So if you don't have it, I can probably post that one table to the to Blackboard. But I think you'll be fine. But again, like the sooner you get the manual, trust me, the better. I've already posted the recording from the lecture during the last lecture on YouTube. So homework 1.1, which is our first actual homework assignment, is going to be assigned today. It is really short, and that'll become clear as we go through the lecture. What we're talking about today is this idea of load and resistance factor design. And so let me preface this discussion by saying this. For those of you that had me for concrete design, I do apologize that this lecture might be boring, because everything that you see in here, we've kind of already talked about in concrete design. But if you've never had me for concrete design, this is going to be brand new. This is basically the philosophy behind which we design steel structures and concrete structures, period. It's the philosophy of structural design that is pretty much now universally utilized. And we'll talk about the differences between it and ASSCE, why ASSCE still is sort of lingering around, and go from there. So I want to begin by going back to the definition of a limit state. So I mentioned this during class on Wednesday, but just to summarize, so a limit state is a condition that we as engineers define that says if the load exceeds this condition, or the element is demanded beyond the capacity of this condition, then it no longer meets the requirements of design. So we had used the example last time of a column undergoing buckling. So here's the column, and I press the column in compression, and then bam, it buckles. And so I can define the capacity of that column based on this phenomenon. And so that could be a limit state. The limit state could be flexural buckling of the column. And so flexural buckling of the column will occur when the load reaches, I don't know, for this maybe 10 pounds. And so when the load reaches 10 pounds, it buckles. And so as long as the load is less than 10 pounds, then I haven't violated that limit state. And so the goal of design would be to ensure that I'm meeting all of those limit states. And so in structural engineering, we have 2 different types of limit states. We have strength and we have serviceability, or strength limit states and service limit states is sort of the terminology we use. We're going to spend today focusing primarily on strength limit states. And so strength limit states are focused on failure, and we need to talk about safety. And more specifically, we need to talk about uncertainty. So how do we ensure safety? How do we ensure that a structure meets a given limit state, both accurately and really the key word is reliably? Okay, so I want to give you a simple example of how we can do this. And there's a very fancy term for this idea. It's what's called a design philosophy. Okay, so let's use a really basic example. Let's say that we have a floor beam in a building system. Okay, so here we are. We're in. Did anybody say something, or the little thing popped up there? If you got a question, let me know. So let's use an example of a floor beam, like the floor beam in this office. Let's say the floor beam that's holding up my office. Okay, so I do the analysis. Let's say I do the structural analysis of all the loads that are on the structure. So the dead loads, the live loads, any other environmental loads that this beam is going to be responsible for, and I draw my shear diagram, draw my moment diagram, do all that, and I find that the maximum moment on this beam is 300 foot kips. I'm just making that number up, okay? Well, the question becomes, am I 100% certain about that number, that 300 foot kips? Can I reliably bank on that? Most structural engineers and most engineers in general will say no. There is some uncertainty associated with that, and that uncertainty comes from a number of places, and we'll talk about that here in a bit. So a design philosophy might be, I'm going to use a factor of safety. And so everybody in this class should know what I mean by a factor of safety. So let's say I use a factor of safety of 2. So all the structural analysis, all of the shear diagram, moment diagram yielded a bending moment of 300 foot kips. Well, if I use a factor of safety of 2, I'll design that beam to support 600 foot kips. So I amplify the bending moment that I get from my analysis by some factor of safety. And then that's the value that I then use to design, okay? And that process, that philosophy in structures land is called allowable strength design. Sometimes it's called allowable stress design, allowable strength design, but that's generally what that process is. Allowable strength design is just a fancy way of using factors of safety, just using a blanket factor of safety to account for all of the uncertainty that's present in the problem, okay? And to be clear, there's nothing on its face that's dangerous about that approach. And there are some arenas in engineering where a factor of safety is the most effective approach. And one of the ones that we experience as civil engineers is the land of geotech. In geotech, the uncertainty is so pervasive. You know, you can do a boring, here and then do a boring 20 foot away and get completely different soil profiles. There's so much scatter and so much variability that just saying, okay, we're just going to use a factor of safety of 3 and move on is fine and is still done to this day. But in structures land, we can get a bit more precise, okay? But in order to discuss that, we need to talk about just the reasons. Why do we even use a factor of safety? I mean, if the structural analysis is perfect and succinct from a static standpoint, why do we even need to do that? Well, there are some problems with ASSCE, and the main purpose of ASSCE and using factor of safeties is to address uncertainty. But while it's simple to use, a single value doesn't address each source of uncertainty. And so here's sort of the example that I like to use to describe the different sources of uncertainty. And so structural engineers tend to look at design from 2 sides of the equation. The one side is looking at the loads, the forces, and the demand that the structure has to withstand. And then there's the resistance, and the resistance is, how strong the structure is, how much load can it withstand. So going back to the issue or the example of the column buckling, the resistance would be, how much force is it going to take to make this happen, to make the column buckle? And then the loads is, well, what types of forces is it going to experience from its use, from the environment, etc. And there's all sorts of uncertainty from either side of the equation. Let me give you a resistance uncertainty. Now, I am of the opinion that any day with controlled demolition is a good day. I like going down to the lab and breaking things. So let's say that we were all back on campus and we were all in, 1103, okay? And let's say we took one of those desks down to the structures lab and we put it under an actuator and we put load in it until we snapped that thing in half. And we just kept amping the load until we broke it. And let's say one of those desks failed at, 600 pounds, okay? 600 pounds. Let me ask you this. Do you think if I failed all of those desks that they would all fail at 600 pounds? Or do you think there would be some scatter? Like one might fail at 600 pounds, one might fail at 605, one might fail at 584, one might fail at 620, one might fail at 615. There's gonna be some scatter, and there's some scatter because there are uncertainties associated with the resistance. So what do I mean by uncertainties associated with the resistance? Well, there's going to be differences in the material quality and the performance from one desk to another. There's going to be differences in the fabrication. I mean, when you fabricate an element, there's tolerances for where the holes are drilled. Even if they're drilled by a machine, machines are accurate to within a given tolerance. They're not laser perfect and precise 100% of the time. There's always a little bit of wiggle room there. There's going to be differences in the construction practice. Are you telling me that every single bolt is tightened to the exact same torque in every single desk? Of course not. There's going to be some scatter associated with the performance of that desk. On the other side, there is uncertainty associated with the loads. One desk might have 10 pounds of books on it. Another desk might have 50 pounds of books on it. Another desk might have 40 pounds of books on it. Another desk might have 20. So there's definitely going to be uncertainty associated with the loads side as well. And the problem with ASD is it doesn't treat those separately. It just says, here's the factor of safety, and just applies it across the board. Instead, we can be a little bit more scientific about it, and we can say, here are the safety factors we need to use for the loads. Here are the safety factors we need to use for the resistances. And so we tend to treat each of those separately, and we factor them according to their own respective uncertainty. And so that philosophy is not called ASD, it's called load and resistance factor design. We factor each of those separately. We take each of the resistances and apply separate safety factors to them. We call those resistance factors, and then we apply different load factors to the different load events. So let me give you an example of what I mean by the different load events. Okay, so two of the most common types of loads that structures experience are dead loads and live loads. Okay, so dead load and live load. Now, let's say I have a beam, and those are the two loads that are present on it. What ASD would do is it would just say the load you need to consider is dead plus live. You just add them up, okay? But LRFD does something different, okay? For those of you that have had concrete design, you probably know where I'm going with this. What we do in or in LRFD is we add each of these up, but each of them are adjusted by a different load factor. So we'll have some factor times D plus some factor times L. Now there are a series of load combinations that we evaluate in LRFD that, and I'll go through those here in a second, but the 7 fun equations, there you go. What you'll find is that the load factors are different for different loads. So one of the most commonly applicable load combinations that we'll see, we use 1.2 for the dead load, but we use 1.6 for the live load. So what that means from an engineering standpoint is we're actually upping the dead load. So we up the dead load by 20%, but we up the live load by 60%. Why do we increase the live load more? Like, why is the load factor higher for the live load than it is for the dead load? Well, it all goes back to uncertainty. I don't know about you, but if I was a designer and I didn't know anything about Marshall University, I didn't know anything about the engineering program or anything, and I'm just designing a university building like the Weisberg Applied Engineering Complex, the outsider looking in, I'm going to be more certain and be able to better estimate the dead loads than I am the live loads. The dead loads, I mean, that's the weight of the steel, the weight of the concrete, the mechanical, electrical, plumbing, the carpet, and all that. I can estimate that. But the live loads, there's so much scatter there, there's so much uncertainty that if I was the designer, I'm going to add a larger I'm going to use a larger factor for the live loads because there's more uncertainty associated with it. That's why we use a 1.6 for the live load and only a 1.2 for the dead. See, ASD wouldn't do that. ASD would just apply a blanket factor of safety and just move on. But we're a bit more scientific in LRFD land, and this is probably one of the most common load combinations we'll use throughout the semester. For those of you that had me for concrete design, we use that all the time. All right. Any questions before we, sort of move on? One thing I will say is before we move on to some of the specific formulas, LRFD uses what's called a reliability-based approach. I am not going to try and get into the land of statistics and start talking about normal distributions and all the different distributions that we use for load events in structural engineering. I'm not going to do that. But what I'll describe is this. So let's go back to the example of the desks. So the desks were, we had, a bunch of desks in one of the classrooms in the building, and we had some scatter, right? We had, a desk that failed at 600 pounds, one that fails at 585, one that fails at 603, one that fails at 612, one that fails at, what have you. We can, if we collect enough data, we can model that with a distribution, right? We can say, okay, here's the mean, here's the standard deviation, and we can model that with a probability distribution. See, one of the things in LRFD is, you do not have a scenario where a structure is perfectly safe. Remember, if you're talking about the normal distribution, you're talking about the bell curve, well, the bell curve goes on forever in either direction. So, on average, the resistances we want to be larger than the loads. But keep in mind that, we're talking about on average and we're talking about bell curves. There is no instance where the structure is 100% perfectly safe. I mean, there are going to be some instances like what we see right here where the loads are on average bigger than the resistances. The point is not to ignore that. The point is to recognize that that is a fact that we can't avoid and to try and manage that and achieve uniform levels of safety. That's what LRFD is trying to do. It's trying to recognize that that's a reality and we've got to address it accordingly. Okay, before I get into the details of LRFD, I want to see if everybody understands the ideas of what I'm talking about. Are there any questions moving forward? Okay, so one of the things that you will see in the manual is whenever you start flipping through the pages, let me grab my manual here and show you. So I'll use my new technology tools here to sort of illustrate this. Let me see. So if you ever open the manual and you start looking through, okay, here's a perfect example. So this is a guide in the manual, and you'll see that there are a series of colors that change. So for instance, there's green items and blue items. The green items utilize ASD. The blue items utilize LRFD. For the entirety of this semester, we're going to utilize LRFD. LRFD has been around since around the 70s or 80s, and it's pretty much the mainstay in modern engineering practice. The only reason ASD even is still printed in the manual is because there are some engineers that have been practicing for quite some time that have been using ASD this whole time and honestly don't really want to change. If I was a betting man, by the time that you all are in your 40s, 50s, what have you, you'll find that ASD has sort of become a memory. In bridge land, it's the only thing that we use. In concrete land, it's the only thing that we use. Steel is one of the only arenas where ASD still sort of shows up in some things, but I think it'll probably vanish in the not too distant future. Okay, so the way that things work in LRFD is we sort of have to make sure that we understand some terminology, and this might seem like a lot on day one, but for one, those of you that have had concrete design know that this really isn't that bad. This is really straightforward. And for those of you that haven't, this is something that we will employ so much that if it seems like a lot now, don't worry, it'll get better as the semester progresses. In LRFD, we deal with factored loads and factored resistances. And so what that means is on the resistance side, what we're going to do is we're going to use the specifications, we're going to use engineering mechanics, we're going to use all the stuff that we have learned in our time in college, and we are going to compute a resistance, a strength of a section based on a given limit state. And then for that strength, we're going to adjust it by a resistance factor. So we have a nominal resistance, we adjust it by a factor, and now we have a factored resistance. And then we sort of do the same thing on the load side. We have all these different load effects like dead loads, live loads, snow loads, wind, etc. We combine those using these statistically calibrated load combinations to get a factored load. So we're comparing factored loads and factored resistances. And as long as the factored resistance is greater than or equal to the factored load, then we know that the structure is safe. And that right there, in a nutshell, is what we're doing this semester, is ensuring that the steel elements we design, the beams, the columns, the connections, the tension members, what have you, we are ensuring that their factored resistance greater than or equal to their factored loads. And honestly, in practice, like the equal almost never happens, because usually your loads, I mean, we're talking about decimals and whatnot, so that it's really just greater than is what you need to focus on. Okay, now, like I said, in LRFD, we have statistically calibrated load combinations that we employ. And in LRFD, there are essentially 7 load combinations that we utilize that are listed here. And so what you would do for every element that you design, like every beam that you design, every column that you design, is, okay, so let's take a beam. Let's take this beam here in this office. So for this beam in this office, the one that's supporting up the loads that's keeping me upright, it's only really experiencing 2 different types of loads. It's experiencing dead load and it's experiencing live load. The dead load being its own self-weight and the weight of the structure, the live load being me, the office, the furniture, and what the structure is being used for. What we would do is we would cycle through these 7 load combinations, and so we would say load combination number 1, what's the answer? Load combination number 2, what's the answer? Load combination number 3, what's the answer? And so on and so forth. And cycle through each one of these, and whichever one yields the worst case answer, the worst case response, that's the one that we're going to use. Now, I have load combination 1 and 2 bolded because in most fundamental everyday designs, load combinations 1 and 2 are probably among the most common. You're really only starting to use the remainder of the load combinations when you get into wind design and seismic design and so on and so forth. And so they tend to not govern as much under normal everyday design. So, if I'm talking about a beam in a building, like the one that's supporting my office, I'm usually either going to do 1.4 times the dead or 1.2 times the dead plus 1.6 times the live. And unless the dead load is, demonstrably bigger than the live load, we tend to use load combination 2 quite a bit. Now, I'm pop quizzing the people in this class. I want to make sure y'all pay attention. I want to see what your thoughts are on this. Tell me when you think load combination 1 would govern. When do you think that load combination 1 would matter more than load combination 2? Like, you can look at it mathematically, but the math should lead you towards a perceived conclusion. Okay, only have a dead load. Or you could say you better have a heck of a lot of dead load in comparison to the live load. That is correct. It's also not really getting at what I'm talking about. When do you think that happens? Like, we build structures to hold stuff up. Live load is what we're designing structures for. So when would a structure experience only dead load? Let me ask it this way. Think about the design life of a structure from beginning to end. When does a structure only experience dead load?
Why did it? Oh.
I think your mic's working, Mr. Adkins.
Sorry, I don't know why.
Not being.
Sorry about that.
Mr. Geis, no, you're fine. Mr. Geis got it right. During construction. During construction, there's no occupancy load in the building. Now, in fairness, if I'm talking about like real world instances, we do tend to apply a construction live load for the workers and whatnot when they're casting the deck or what have you. But in those instances, you can find that the dead load effects far exceed the live load effects because there aren't any live loads because it's being built. So one of the other things I do kind of want you to think about is there are limit states that can affect a design that aren't just during its completed stage. Sometimes the worst case design situation is while the structure is being built. For instance, in bridge engineering, you can find that there are instances where the worst case limit state is actually the stresses that it endures during construction, not when it's complete. Because while it's being constructed, the elements themselves are weaker. You know, it's like if you're putting together an erector set, sometimes you'll find that the structure is kind of flimsy until it's finally put together, and then it's strong. So its actual less stable state might be while it's being built. I saw a comment. I didn't see what's that. Yeah, it's why you have to use shoring during concrete. You know, you shore up the flooring system, and shoring versus unshored construction is a big thing in structural engineering because shoring can be expensive, and it's a big trade-off. Yes, sir, Mr. Atkins.
So in this case, we might as well use like temporary support structures to hold the whole thing up as we build it to ensure stability so it doesn't compromise itself.
Well, okay, this is a wonderful discussion to have because what you're talking about is there's a trade-off there. So, for example, let's take shored versus unshored construction just to explore the aspects. So, when you're using unshored construction, in other words, no temporary supports, no temporary formwork or whatnot, the structural beams themselves would probably have to be bigger because they have to support the wet concrete by themselves. So the in condition structure, like the structure once it's complete, will probably be bigger than if you used shoring. But shoring takes time. It takes time and effort and energy to put together. And shoring doesn't just magically show up on the construction site. Somebody has to put that together. And that's time, labor, and money that went into something that isn't even going to be part of the structure when it's finished. So it's a trade-off, you know. If you use shoring, the structure can be lighter, but then you have to pay somebody and spend the time shoring it. If you use unshored construction, it can go faster, but the structure's heavier. Which one do you use? Well, it depends. It depends on the project, depends on the conditions, depends on the economy. So, but you kind of need to understand how to do both. This is structural engineering. This is what we're talking about here. I love this. This is great. This is good stuff. Any other questions before we sort of jump into some of the load types? On this Twitch stream, I've got the stream pulled up on this other computer. It's a little strange to see the interface like this.
I'm good to go when you.
All right, let's talk about the structural load type. All right. As I was saying, the ghost race. As I was saying, there are some loads that you're not going to see reflected. Like for instance, R. R is the rain load, and with adequate drainage, you can neglect rain loads because the snow loads that accumulate and stay on the roof will tend to be heavier anyways because they're permanent and they're stationary. The other, like L sub R is a live load. It's just the live load on the roof. Like for instance, if you look at load combination 3, what load combination 3 is saying, you've got 1.2 dead, and then you've got 1.6 times essentially whatever the maximum effect on the roof is. It's either the live load on the roof, so the live load on the roof would be like construction or maintenance or workers or whatnot, snow or rain. And I'm gonna really the one that's critical and the one that's sort of tough to understand is the snow load. So that's why I'm sort of moving past that. And it 99 times out of 100 ends up being what governs anyways. So let's talk about really the 5 really critical effects that we need to deal with. 3 of them act in the direction of gravity, so up and down. So that's dead load, live load, and snow load. And then the other 2 are the lateral effects. They're the ones that act side to side, and that's wind and earthquakes or seismic loads. Now, I am not going to talk about ASCE 7 directly, but I do want to mention ASCE 7. So some of you have probably heard of the International Building Code. Some of you might have heard of ASCE. So ASCE does a whole lot more than sponsor the concrete canoe competition. They serve, in addition to student outreach and student engagement, and in addition to the lobbying and the governmental outreach that they do, they serve as one of the largest governing bodies for some of the standards that we use when designing civil engineering systems. And they publish standards from all sorts of arenas for water, wastewater, transportation, and structures. One of their most common guides and one of the most referenced guides that ASCE publishes is ASCE 7. ASCE 7 is the guide on the minimum design loads and associated criteria for buildings and other structures. It's where we specify what the design loads are. Like, for instance, if you're designing a building in Huntington, West Virginia, what's the snow load? Do you know what the snow load is? And without some agreed upon standard, Harrison might use a different snow load than Trevor. Trevor might use a different snow load than Gordon. Gordon might use a different snow load than Zach, and so on and so forth. The standard ensures that we're all utilizing a common approach when designing. And it's also, based off of the data and whatnot. We're not going to use ASCE 7 directly, but we are going to use some provisions throughout the semester. We'll refer to, the basic load types, the load combinations that I just showed, that comes from ASCE 7. And as we get later on, we might do some things related to live load reduction for beams and whatnot, and we'll talk about that as we progress. So first off, let's talk about dead loads. Dead loads in, most applications are the loads that are, specifically they're the loads that are permanent, that are stationary, but in most practical applications, we're talking about the structure itself, its own self-weight, any other attachment that's permanent that's not going anywhere. So dead loads are stationary. They're part of the system. Many of these you can look up. You can look up like floor loads and roof loads and so on and so forth, but most civil engineering structures are made out of steel and concrete. The unit weight of steel is structural steel is 490 pounds per cubic foot. So if I have a box of steel that's yay big, yay big, yay big, and it's, full solid structural steel, it weighs 490 pounds. 490 pounds per cubic foot is a number I want burned into the back of your head by the time you graduate as a civil engineering student. It's just a number you need to know. It's like the unit weight of water being 62.4 pounds per cubic foot. It's a number that you kind of need to just know. Concrete, obviously concrete is a material that can have a variable weight, depending upon your mix. You can have lightweight concrete, you can have what have you, normal weight concrete, same lightweight, all that. And a typical upper bound value for reinforced concrete, so concrete with reinforcement in it because the steel is heavier, a typical value that's used is 150 pounds per cubic foot. When in doubt, 150 pounds per cubic foot is a very valuable or a very, very, very adequate and accurate value for estimating the weight of reinforced concrete. And so unless otherwise stated, if throughout the semester I mentioned, I have a slab that's, 6 inches thick, and I don't say, what the weight of the concrete is, assume 150 pounds per cubic foot. All right. And again, ASCE 7 and similar guides will put out, okay, let's take this floor. So this floor has carpet, or it might have linoleum tile. There's the fireproofing, the metal deck that's used as the formwork, the mechanical, electrical, and plumbing allowances, all that stuff. You can look that stuff up either from the manufacturer or ASCE 7. For those of you that had me for structural analysis last semester, remember these loads, see how they're listed in PSF? Remember how we would take tributary area and then collapse that into a line load and then use that to distribute? So you could sort of see the connective tissue between this and structural analysis last semester. Now let's talk about live loads. Live loads, it's a very simple term like dead loads and live loads, but really what I like to use is the term occupancy. Live loads represent what the structure is being used for. So the live loads in a hospital are going to be different than the live loads in a school, and different than the live loads in an office building or a theater or a what have you. So if we were in person, I say we are a live load acting on this classroom. If we were in person, we would be the live load. Whatever the structure is being used for, that's going to sort of dictate what you're designing for. And live loads can change not just depending upon the type of structure, but where you're at in the structure. So for instance, if you're designing a hotel, you're going to use different live loads for the rooms than you are the hallway. The hallway tends to have a more dense collection of people in it, so it tends to have a heavier load. Also, whenever you're designing, the loads that you can use can depend on the type of structure. So for instance, if you're designing a hotel, the hotels don't really change very much in terms of their layout. Like the layout of the hotel is very set in stone. Here are the hallways, here are the rooms. When you're designing a commercial office building, for example, typically structural engineers will design the entire floor system as if it's one big hallway, because the developer wants to be able to sell off, I'm going to sell or rent this space out at so many dollars per square foot. And so if some, dentist says, I need this much space to open up my dentist's office, the developer doesn't want to say, okay, well, the hallways have to be here and the offices have to be here. He wants to be able to tell the dentist, you arrange it however you want. So they tend to design it as one big hallway. It just depends on the project. But again, that's where the standards come into play. You would just look these values up from a standard so that we're all using agreed upon values. Like for instance, the live load for libraries tends to be like 150 pounds per cubic foot. We use a heavier load because of all the books. So again, reflective of the type of structure that you're designing. All right, any questions before we go on to some of the environmental effects? Okay, now there are three really controlling effects that are a result of the environment. The first is snow. Snow is dependent, obviously, on where the structure is located. To give you an example, this is a snow map from ASCE 7. This is the snow map for the snow loads in the United States. One state has its own snow load map. There's a snow load map for the country, and then a snow load map for this one state. What state do you think I'm talking about? Which state in America would have its own snow load map?
California, 100%.
Alaska.
No, Alaska. Snow in Alaska is going to be different. And besides, Alaska or California is right there. Now, yeah, if you're working in Florida or South Florida, yeah, that's going to be a little different. The snow loads obviously are representative of the geography. There are tools online, like for instance, hazards.atcouncil.org. What they've done is they've taken all of the snow load or all of the environmental load maps in ASCE 7 and then digitized them and sort of integrated them with Google Maps. So if you could say, I'm designing a structure here, that's the snow load, and so it'll look it up for you. Obviously, as you get farther north, the snow loads are going to get higher, and you can see in the map the variability. But I don't know about you, but that's one of the beauties of having these tools like this AT Council website, because I can't read that, but you don't need to. That Google Maps integration, it takes care of it for you. What about wind loads? Well, first off, this is the wind load map for the United States. Why is there so much of a change in the wind loads along the coastal regions? Why? I mean, like the bulk of the country has a common wind speed, but then along the coast it gets all different. Why?
The mountains.
It's what Courtney said. Hurricanes. That's yeah. Now you I don't know who mentioned mountains, but there actually are some regions in the United States where you can have some wind speed up effects. There's like these special wind regions. I don't know if you see that little gray shaded region right here, but there you can have some wind speed up effects in based on various topography, but the wind speeds will become higher as a function or near the coast because of hurricanes. One of the other things that pops up and I don't know, I don't remember if I put it in these slides or not, but one of the other things that pops up with environmental loads is what's called a risk category. So there are 4 risk categories. Let me see if I put those in here. No, I didn't. I'll just sort of give you the brief overview. So there are 4 risk categories assigned in ASSCE 7. Risk category 1 are unmanned structures like grain silos or abandoned or empty warehouses and stuff like that. And the risk category increases as a function of the structure's contribution to society. So like risk category 3 would be like schools, theaters, nursing homes, any hospital or nursing homes, any place where the people inside might have a tough time getting out on their own. Like if there's an emergency in a theater, it might be difficult to get everybody out all at once because of the emergency. And risk category 4 is like police, fire stations, hospitals, 911 call centers, anything where if the structure fell down, that's going to impact like everybody. Like if the hospital experienced a structural failure, that would affect the whole city. What you'll find with environmental effects is we actually increase the environmental effects based on their risk category as well. So that's not here in this diagram, but these are wind speeds, I believe, based on risk category 2. I can't remember. I think that's risk category 2. And if it was 3 or 4, the wind speeds would be even higher. Would dams or bridges be in a risk category? The bridge spec handles that a little bit differently, but there can be instances where you might need to account for that. The other thing that can affect both dams, bridges, and buildings, and this is really where it gets interesting, is the 5th and final load, which is earthquakes. Earthquakes are a little different. We don't have to really so much worry about earthquakes here, but earthquake design is really when you have to roll up your sleeves and affect things. I would argue that from a structural engineer's perspective into what's challenging, what's complicated, wind and seismic is really what makes things complicated. For example, one of the things that makes wind and seismic complicated is that wind engineering and seismic engineering gets more difficult as the buildings get taller. Like, to put it in perspective, okay, I'm on the 2nd floor of the engineering building, and so a structural engineer designed the floor beams that are supporting my office. Well, above me there is a series of, I think it's like Dr. Begley's office is like right above mine, and he has floor beams supporting his office. They were not designed any differently. The methodology was the same. Designing a floor beam for gravity loads on the 2nd story is the same as designing floor beams on the 82nd story. It's not any different. But wind loads change because as the building gets taller, the lateral stability gets more complicated. If anybody in this room, I'm curious if anybody has been on the top of the Empire State Building on the observation deck, and if it was windy when you were out there. I'm just curious.
I've been on the Sears Tower, and it was always windy in Chicago.
Wait, did it feel wavy up there?
I mean, like it similar, but it's not like you're in a tree. It's like, I don't know. You can sense that it's moving though.
And that's, see right there, it's the lateral effects, the wind and the seismic. That's what makes tall building design complicated, because if all we had to account for was gravity, I mean, designing for gravity loads is no different on the bottom story than it is on the top. I mean, as the building gets taller, it gets heavier, but that doesn't make it more complicated. And yeah, I mean, whenever you go up on a tall building, the wind loads are pretty significant. And wind loads can get really funky because you can have different pressures on one end. You can have negative pressure inside a building. Like, have you ever been in a building and it's a really windy day and the doors like suck in, you know, or they won't close all the way because the building's getting hit with wind? You can generate different pressures inside the building. Like, it can get wind and seismic can get really, really weird. Like seismic events, they don't really cause loads on a building, but they cause acceleration. So, you know, the ground is moving, the building is heavy, the building is being accelerated. So it's experiencing, you know, that force equals mass times acceleration. We use that to develop equivalent loads that we would put into a RESA model for design. Obviously, you know, earthquake loads are a function of where we're at. You know, we don't really have to worry about them so much here. But if we're in California or in Alaska, or even, you know, like in Western Kentucky, the hazards that could be generated from an earthquake are pretty significant. So, you know, fortunately, again, this is where all the specs come into play. You know, you can, based on your location, look up ground accelerations, and then, you know, through a series of adjustments and computing the weight of the building, you can come up with loads on the building and take it from there. But it gets it, you know, you really do have to roll up your sleeves and you have to understand, you know, what you're doing. Any questions? I want to pull something up real quick before we call it. Oh, sorry, hold on.
So when you were talking about how the beams were same for your office as Dr. Begley's, can you evaluate on that a little bit more? Like, I thought.
Well, so.
Oh, go ahead.
No, go ahead. No, you go ahead.
I thought it would be like probably your bottom, either like vice versa. Like one would be bigger than the other to either support all that load or, you know.
So a couple of things. If you go back to what we did in structural analysis last semester, you know, if you have a floor system and that floor system is subjected to a pressure load, then the bending moment on a beam is a function of really only two things: how long that beam is and how far apart the beams are spaced, right? If those dimensions are the same on the second story than they are on the third story, then the loads aren't going to be any different. Because it's not like somebody looked at my office and said, well, we're going to design Dr. Michelson's office for 50 pounds per square foot, but Dr. Begley's we're going to design for 100 pounds per square foot. They're both offices, so they're both going to be designed for the same load demand, okay? As long as the structural geometry is the same, then the beams would be designed the same way. Now, it is possible that there's a couple things to point out. It's possible that the framing plan is somewhat different on the third floor, that maybe the beams are longer or shorter, and so you know, locally that results in different designs. So that's possible, but you know, barring that, the beams would be the same. The other point I'd mention is there is a difference between the beams and the columns. Okay, now the columns, you know, as you go down the building, the columns are experiencing heavier load because they're having to hold the building up. So the columns on, you know, the third story are going to be smaller than the columns on the first story, because the first story has got to hold everything up from under it, right? So
okay,
you know,
yeah, I understand now. That helped. Thank you.
No problem. I do want to pull something up real quick. I just want to show you your homework assignment for Monday. Again, it's really short. I'm just giving you a couple of, you know, dead load moment, live load moment, snow load moment, and a wind load moment. I just want you to go through the load combinations and determine the factored load. And so part of this is to introduce you to the load combinations and introduce you to the terminology. So in structures land, we don't really care about the nominal dead load moment or the nominal live load moment. We care about the factored moment. The factored moment being the worst case scenario from these load combinations. 2 points I'll mention before we call it. Some of you might be looking at these combinations and you might go, wait a minute, why is the load factor for wind 1 on some of these? Why is the load factor for seismic 1? The reason why is because LRFD is becoming such a mainstay that all of those maps that I showed you already have the load factors built into it, so you don't have to use them. That's why LRFD is really like the way that we should be doing things nowadays. The other thing is, if you just take a second and look at some of these equations, like for instance, I didn't give you a seismic load, an E value. So the seismic load would be 0. Before you start just grunting out all of them, you can probably by observation skip a few. And I'll give you one as an example. Let's take 1 and 7. So if there's no E value, the difference, like which one's going to control between 1 and 7? It's going to be 1, because I mean, you can just look at it and see that 1's going to give you a worst case answer. So you don't need to do 7 if you don't want to. So if you review it a bit, you can probably save yourself some work. Okay, that's going to be due Monday. It's a really short assignment. I honestly, other than barring calculator issues, I don't see anybody having any problems with it. And if there's any other questions, I'm just curious. Anybody have any other questions?
None that immediately comes to mind.
All right. Well, that's all I have, everybody. Hopefully you enjoyed my Twitch stream. I will see you all on Monday. You all have a wonderful weekend. You like that stream better. All right, we'll see you, everybody.